Faraday's Law of Induction. Michael Faraday and Joseph Henry showed that a changing current will induce an EMF, which then will create an electric current in a second loop. And what's interesting here is Faraday did this in the UK and Joseph Henry in the US fairly simultaneously, but Faraday got his results out first. Their initial experiments showed that a changing current generates a changing magnetic field, which develops an EMF and current. But what is actually changing is the magnetic flux. Faraday's law of induction states that the induced EMF in a wire loop is proportional to the rate of change of magnetic flux through the loop, right here. A few words about Michael Faraday. Michael Faraday made some of the greatest contributions to physics in history, focusing on electricity and magnetism and their interactions. Albert Einstein kept a picture of him, along with pictures of Sir Isaac Newton and James Clerk Maxwell in his study. He only had a basic education and no mathematical training beyond basic trigonometry. He had fantastic vision and scientific creativity and was a superb experimentalist. It remained for Maxwell to put a mathematical formalism behind Faraday's concepts. He was also responsible for creating field theory, which was then used extensively by physicists in the 20th century and today. Now let's look at the equation. N is the number of loops or turns of wire in the coil. Delta flux B is the change of the magnetic flux. Either the area of the loop exposed to the flux can change, or the magnitude of the magnetic field. And finally, delta T is the time interval over which the flux is changing. The negative sign is related to the direction of the induced EMF, and we'll discuss that later. For now, we'll focus on the magnitude of the induced EMF and we'll work an example problem. Faraday's law can be modified if either the magnetic field or the cross-sectional area of the loop is constant. So first let's take where A, the cross-sectional area, does not change. Then here's our equation, and that's going to be flux B final minus flux B initial. And then what do we do then? We say, what is flux equal to? Well, that's B times A. So that's what we have here. Since the area does not change, we can say that A is equal to A sub F equals A sub 0. We will make that substitution here. You factor out the A, and then we're left with a change in the magnetic field. So the equation is negative NA delta B over delta T. We'll use the same approach, but this time the magnetic field will be held constant and the cross-sectional area will change. So we've already done this on the last slide, all these steps, and also this step. This time the magnetic field does not change, so we'll say that B without a subscript equals B final equals B initial. We make the substitution over here. We see that we have B in both terms. We factor it out, and then we have minus NB delta A over delta T. So far in the problems, we've dealt with the magnetic flux changing due to the magnetic field decreasing or increasing. Now recall, flux is equal to B times the area, and changing flux is what generates our EMF. So we can either change the magnetic field or the area and generate an EMF. So how do you change the area? Here's a pretty simple case. You have a loop of wire here. It has a certain cross-sectional area exposed to the magnetic field. If I were to pull it apart, I now have a smaller area. So in this case, the area goes down, so the magnetic flux decreases. There's another way of changing the area in order to change the flux. It's a little more practical than the hand stretching it that we just showed. We can take a coil of wire here, put it on little pivot points here, and rotate it. When you do that, the flux through the area will decrease. We'll have less of an area exposed to the magnetic field. So we have the loop being rotated from being perpendicular to the field to parallel with the field. So the flux goes from a maximum to 0. We'll be covering this in more detail when we get to AP Physics, where we worry about what happens between this perpendicular nature here to the parallel. but in both those cases the area exposed to the magnetic field is decreasing, so the flux will decrease. Find the magnitude of the induced EMF in an 8 square meter one-loop coil if it is perpendicular to a 0.40 Tesla magnetic field that decreases to 0.0 Tesla over a time interval of 2 seconds. We start, as always, by listing our givens right over here. And here's the one loop. That means that n is equal to 1. We calculate our initial flux equation right over here, B times A, and it's perpendicular, so we can take the full value of the magnetic field in the area, and we get 3.2 Webers. Then we calculate the final flux, and since the magnetic field is 0, so is the magnetic flux. Now we find our change in magnetic flux, which is final flux minus initial. We get 0 minus 3.2, so we get minus 3.2 Webers. Now we want to find the EMF, and we just do the absolute value here. We're not interested in the negative sign. We just want to find the magnitude. So we substitute in our givens and the delta flux that we just calculated, carry out the math, and we get 1.6 volts. Example 2. A rectangular loop of wire with an area of 0.048 square meters is perpendicular to a magnetic field. The magnitude of the field changes uniformly from 0.24 Tesla to 1.67 Tesla in 0.25 seconds. What is the magnitude of the induced EMF in the loop? We list our givens, and then, since all we say is there's a rectangular loop of wire, we assume that means just one loop, so n is equal to 1. We have Faraday's law for a constant area, and our change in the magnetic field is right over here. It's just 1.67 Tesla minus 0.24 Tesla. And notice we want the magnitude of the EMF, so we put the absolute value sign on both sides of the equation, calculate out our mathematics, and we get the magnitude is 0.27 volts. A circular wire loop with a radius of 9.0 centimeters is initially parallel to a uniform magnetic field of 2.6 Tesla. The loop's orientation is changed so that it is perpendicular to the field in 0.12 seconds. What is the induced EMF in the loop? First, we write out our givens. And let's be very careful with the radius here. It's given in centimeters, but we need to use meters to solve the equation. So we move the decimal point over 2 places to the left. Here's our area of a circular loop, 4 pi r squared. We plug in our values, and we get the area is 0.025 square meters. Now, the initial flux is 0 because the loop is parallel to the field, and the final flux is at its maximum value, which is just B times A. Substitute in the givens, and we get a final flux of 0.065 Webers. We use Faraday's law, which is EMF is minus n, which is the number of loops, times the change in flux over time. We substitute in our givens. We only have one loop, so n is 1. Here's our final flux, initial flux, and time. And we get the absolute value, or the magnitude of the EMF, is 0.54 volts. We're not going to worry about the negative sign here because we're looking for the magnitude, and the sign is part of Lenz's law. That tells us what direction the induced voltage will be. We're not going to worry about that for now. A circular loop is made of a flexible wire. The loop is perpendicular to a uniform magnetic field with a magnitude of 3.5 Tesla. The area of the loop is changed from 0.005 square meters to 0.008 square meters in 0.15 seconds. What is the induced EMF in the loop? We can now use Faraday's law, and since the magnetic field is constant, we can pull it out to delta flux over delta T. So we're left with minus NB delta A over delta T. We then substitute in our givens, right over here, carry out the math, and we get a magnitude of 0.07 volts.